Hello students, welcome to Joint Chemistry. Today's lesson is Basic Information of Coordination Compound. From today, we are going to start a chapter is Coordination Compound. Okay, so this is the part 1 of this chapter where we will learn some basic information. Now, what is coordination compound? Before understanding what is coordination compound, there are some reaction. Let's see. Now, if we mixed these salts together, we will get these additional compounds. Okay. Now, in case of K2SO4, Al2SO4 whole 3, we get potash alum, which is K2SO4, Al2SO4 whole 3, and 24H2O. Okay. Obviously, in water solvent, we are mixing this salt together and we get these addition products. In case of this NH4 whole 2SO4, FeSO4, and 6H2O, we get FeSO4 and NH4 whole 2SO4 is 6H2O. This is a more salt. This is an addition compound. Okay. In case of copper sulfate and NH3, we get tetraamine copper sulfate. In case of FeCN whole 2 and potassium cyanide, we get potassium ferrocyanide. Okay. Now these addition compounds are two types. One is double salt, another one is coordination compound or complex compound. Okay, so one is double salt, another one is coordination compounds or complex compounds. Now, what is double salt? These double salts are stable in solid state but lose their identity in water solution or in polar solvent. Okay, in water or in any polar solvent, they dissociate in individual ions. For example, K2SO4, Al2SO4 whole 3, 24H2O, which is potash alum. This potash alum dissociate in water, in polar solvent or in water, dissociate into like K2SO4 dissociate into potassium plus and SO4 minus 2, and this Al2SO4 whole 3 dissociate into SO4 minus 2 and aluminum plus 3. Okay, aluminum plus 3. So this potash alum dissociates into their individual ions, fully dissociate into their individual ions in polar solvent. So these are double salt. Now what is coordination compounds? The coordination compounds retain their identity in solution. They does not give all its constituent ions. For example, copper sulfate, this tetraamine copper sulfate, it dissociates in polar solvent into these two ions, where this tetraamine copper ion is known as complex ion. Okay. In case of K3FeCN whole 6, it dissociates into potassium plus and these ion, which is another complex anion because it contains negative charge. That is why it is anion. Okay. Now there are some neutral complexes like this platinum NH3 whole 2 Cl2, nickel carbonyl, and etc. It is tetracarbonyl nickel. Okay, the CO, it is known as carbonyl, does not give any ions in aqueous solution because they are neutral complexes. As they are neutral complex, they does not dissociate in any polar solvent. Okay. Now what is this complex ion or complex anion? Now, it is a positively or negatively charged species which contains a central metal ion or atom with a suitable number of ligands surrounding the central metal ion or atom. Okay, so this is these ions, these anions or these ion is a positively charged or negatively charged ions which contains the metals and surroundings with the ligands, right? So these are nothing but a group of ions they which does not further dissociates in polar solvents. Okay, and that's why these compounds are known as coordination compounds, and these ions are known as coordination ions or complex ion. Okay, now these coordination compounds made of these two parts. One is metal ion, sometimes metal atoms, and ligands. Now this metal ion generally positively charged, sometimes neutral, accepts electrons. So according to the Lewis acid base concepts, these metal ions accepts electrons. That's why they're known as Lewis acids. Okay, generally metal ion means Mn plus. This N can be any integer. Okay, Mn plus means containing positively charged. So as they accept electrons, that's why they're known as Lewis acid. And ligand can be negatively charged or neutral, or sometimes it is also positively charged. They donate electron. There are some exceptions, I will talk about it later. So basically they donate electrons. So according to Lewis acid base concepts, ligands are Lewis base. So metals are Lewis acids because they accept electrons, and ligands are Lewis base because they donate electrons. Okay, so these are two parts of coordination compounds. Now we should know some other terms, which is coordination number. What is coordination number? The total number of donor atoms attached to the central metal ion or atom is known as the coordination number. Now you should remind this, the number of donor atoms, the total number of donor atoms. Okay, the total number of donor atoms attached to the central metal ion or atom is known as coordination number. Or we can say the total number of sites at which the ligand is attached with the central metallic atom or ion. Okay, the total number of sites at which the ligand attached with the central metallic atom or ion, okay, is known as coordination number. By this coordination number we can predict the geometry of the compound. When it is coordination number 2, then the geometry is linear. When it is coordination number 3, the geometry is trigonal planar. When it is coordination number 4, the geometry is tetrahedral or sometimes square planar. When it is coordination number 5, the geometry is trigonal bipyramidal or TBP, denoted as a TBP. When it is coordination number 6, the geometry is octahedral, which is OH. When it is coordination number 7, the geometry is pentagonal bipyramidal. Okay. Now there are some other terms, which is coordination sphere and ionization sphere. Now what is coordination sphere? In structural formula, the square bracket is called coordination sphere. Like you can see cobalt NH3 whole 5 Cl into a third bracket, then Cl2 outside of this bracket. Now into this third bracket area is known as coordination area or coordination sphere. Okay, and outside of this third bracket is the ionization sphere. So outside of the sphere is the ionization sphere, means outside of the bracket. Okay, outside of the bracket is known as is known as ionization sphere, and inside the bracket area is known as coordination sphere. Now let's talk about ligands. So there are some classification of ligands on the basis of different character. Now at first, on the basis of charge, we can classify the ligands into one neutral ligand, another one anionic ligand, and another one cationic ligand. Now what is neutral ligand? As you can see, there is a water NH3 NH2OH. This contains only lone pair but no charge. So that's why they known as neutral ligands, and they donate electrons by their lone pair. Okay. In case of anionic ligands, they contains minus charge on their head, right? Or in case of cationic ligand, they contains positive charge on their head, right? Now, on the basis of donor atoms, number of the donor atoms of the ligands, or we can call it denticity. So what is denticity? Denticity of the ligand is the number of the donor atoms. At first, monodentate ligands. In case of monodentate ligands, it contains only one donor site. Okay, so number of the donor atoms in case of monodentate ligand is 1. Now there are some examples of monodentate ligand. At first, some neutral monodentate ligands. This is C2H5 whole 3 N, which is known as triethylamine. This is C6H5 whole 3 P, which is known as triphenylamine. Now NH2OH, which is hydroxylamine, CH3NH2, which is methylamine, C5H5N, which is pyridine, PCl3, which is phosphorus trichloride, CO, which is carbonyl, NO, nitrosyl, H2O, aqua, NH3 amine. So these are some neutral ligands, monodentate ligands. Okay. Now here it is the anionic monodentate ligands. Anionic means contains negative charge. So this is F minus known as fluorido. Okay, known as fluorido. In case of Cl minus, it is known as chlorido. In case of CH3COO minus, which is known as acetato, and this is NH minus 2, which is known as imido. So as we can see, the names are little bit different because these are the names which use in IUPAC naming of coordination compounds. Okay. Now there are some other examples of monodentate ligands. Okay, these are some anionic monodentate ligands. This one O minus 2 is oxido, OH minus hydroxo, O2 minus 2. This is like this. O minus bond O minus is paroxo. This one O2 minus 2, sorry, O2 minus is superoxo, CO3 minus 2 carbonato, CN minus cyano or cyanido C. It means when it bonded with the C side is cyanido C, and when it bonded with the N side is cyanido N or isocyanido. Okay, so there are some cationic monodentate ligand which is NO plus nitrosonium. Okay, this now the bidentate ligand. Bidentate ligand means containing two donor site. Okay, bidentate ligand means containing two donor site. Now there are some neutral bidentate ligand. First is CH2CH2. There are two NH2 groups, which is ethylene diamine. Symbol is small en. Okay, now there these two pyridine moiety attached to it at the 2 position, right? This is the 2 position. They are attached by this 2 position is known as 2,2 bipyridine. Symbol is BPY. Now this is CH2CH3, and there is a 2 NH2 group at the 1 and 2 position, which is 1,2 diaminopropane. Symbol is PN, and this is a fused ring which is 110 phenanthroline. Symbol is OFEN. So these are all neutral and bidentate ligand. As we can see, they all have two donor site, right? Now when in case of bidentate ligands, one is neutral site and another one is anionic site. Some examples are, this is acetyl acetonato ion, symbolized is ACAC, and this is dimethylglyoxymato, symbol is DMG. Okay, dimethylglyoxymato. And this is an example of bidentate ligand containing both of the donor sites is anionic. It is oxalato. Okay, so these are some examples of bidentate ligands. Now here this is some example of tridentate ligand. Is this is CH2CH2, and there are 3 NH2 groups. The compound is triaminopropane, and this is NH2 CH2CH2 NH CH2CH2 NH. This is known as diethylene triamine. Okay, so diene. This is diethylene triamine, which also contains 1, 2, 3, 3 donor sites, and all are neutral. Okay, all are neutral, 3 donor sites, so they are tridentate ligand. Now next is tetradentate ligand. As you can see, NH2CH2 NH CH2 NH CH2 NH CH2 NH2. In this case 1, 2, 3, 4, 5. Okay, so this is not tetradentate ligand, this is pentadentate ligand. Let's see some tetradentate ligand. If we see this one, Okay, as we can see here, there is a 1, 2, 3 and 4 nitrogen donor sites. So that's why it is tetradentate ligand and named as known as triethylene tri this is known as triamine triamino triethylene triethyl amine. Okay, so this is known as, this is a structure where you can see it is a 4 nitrogen donor site. The name is triamino triethyl amine. Okay, and this one is the pentadentate ligand. Pentadentate ligand, which is NH2 CH2 whole 2 NH CH2 whole 2 NH CH2 whole 2 NH CH2 whole 2 NH2, which is known as tetraethylene, which is known as tetraethylene pentaamine. Okay, which is known as tetraethylene pentaamine. Symbol is tetra-En. Now there is a important ligand which is hexadentate ligand. This is the structure of the hexadentate ligand, which is ethylene diamine tetraacetate ion, or commonly known as EDTA. Okay, EDTA 4 minus. So this is the structure of the EDTA, where you can see there is a 1, 2, 3, 4 oxygen donor site and 2 nitrogen donor site. So overall it is a hexadentate ligand. Okay, so these are all ligands which are classified on the basis of their denticity or number of the donor atoms on the ligands. Now there are some another kinds of ligand. This is ambidentate ligand. Now these ligands have two or more than two donor atoms. Such ligands can coordinate to the metal atoms or ions through any of their atoms at a time. That means they have more than two donor sites, but they cannot donate at the same time. Okay, like for example NO2 minus, it contains N donor at site. Okay, and also oxygen donor site. Now when it donates from N side, it is known as nitro. When it donates from O side, it is known as nitrito. Okay, so these are two sides, two different sides. Okay, that's why this is known as ambidentate ligand. There are some another example, that is SCN minus. When it donates from the sulfur side, it is thiocyanate. When it is donated from the nitrogen side, it is known as isothiocyanate. In case of Cn minus, when it is donated from the C side, it is known as cyano. When it is donated from the N side, it is known as isocyano. Now, flexidentate ligands. There are many ligands which have more than one donor atoms, commonly known as polydentate ligand, can coordinate with the metal through one donor atom or through both of its donor atom at different conditions. For example, SO4 minus 2 and CO3 minus 2. Now, in case of CO3 minus 2, the structure is like this. Okay, so it has two donor sites, right? So it can bind with the metal atom or ion by with one of its oxygen donor atom or through both of its oxygen donor atom. Okay, so due to this kind of flexibility, it is so flexible that it can change their denticity or number of the donor site. That's why they known as a flexidentate ligand. Okay, so same as for SO4 minus 2. If we draw the structure, this is the structure of SO4 minus 2. Okay, so it is also contains two oxygen donor sites, so it can change its denticity. That's why it is known as flexidentate ligand. Now there is a very unique and very special kind of ligand, is pi acid ligand. Now there are some ligands which donate electrons to the metal atom and also accept electrons from metal simultaneously. and these kind of ligands are known as pi acid ligands. Now due to this unique name pi acid, I'm going to tell you why it is named like this pi acid. Okay, now the examples are CO and PR3. Now in case of if we see the CO ligand, the mechanism is something like this way. Okay, I draw a very simplest form of this mechanism to understand it. Now if we see the metal accepts the electrons from the CO to its vacant orbital. Okay, then the CO ligand accepts electron from the metal's electron filled orbital, okay, to its vacant orbital. Okay, so when it donates electron, at the same time it accepts electron from the metal atom. So this way it works, and this way it binds to the metal atom, and this whole mechanism is known as synergic mechanism. Okay, so these are all classification of the ligands and some examples and their names. So you should remember the name of these ligands because these names will use in IUPAC naming of the coordination compound. Okay. In the next class, I will discuss about the how to calculate the metal charge of the coordination compounds and also IUPAC naming. Okay. So see you in next video, and please like, share, and subscribe. Thank you.